Hello and welcome to this section of the Calculus Derivative Help Tutor. In this section we're going to tackle the topic of how to take a derivative of a general exponential and a general logarithm. And what I mean by that is in the last two sections we've done the natural logarithm, which was base e logarithm, and we've done what we call natural exponential, which was an exponential with a base e. So e to the x and logarithm of x. That's what we did in the last two sections. This section we're going to loosen the belt a little bit and get more general, where we can have exponential functions of different bases and we're going to have logarithms of different bases. But what we're going to find is that they're going to be a little bit related to what we've already learned. That's why we learned the special case first. Now we're going to come and learn the more general case. So what do I mean when I say a general exponential? A general exponential is usually written as a to the power of x, where a is a number. Now you might look at this at first glance and say, well, I know how to take the derivative of that. We did that in the very first part of Calculus 1. Well, not really. What we did in the first part of Calculus 1 was x squared. That's variable on the bottom, exponent on the top. That's not what we have here. Here we have something more like 2 to the power of x, where a is any number you want to pick. It could be 3 to the power of x, 15 to the power of x, negative 2 to the power of x, whatever. But it's different because here we have x to the power of a number, and here we have a number to the power of x. This is what we're studying in this section. We have not learned how to take the derivative of that function yet. We've learned how to take x squared, x cubed, x to the fifth. We've never learned how to take 2 to the power of x or 3 to the power of x. So that's what we're going to be doing here. So this is an exponential. Now the derivative I'm just going to write down without proof, and then we'll work a lot of problems just like we did in the last section. So the derivative with respect to x of the function a to the power of x, where remember a can be any number you really want it to be, is equal to a to the x, okay, times natural log of a. So here we have, let me draw some parallels. The derivative of this general exponential yields the same exponential back. So it is indestructible to a degree, just like the regular e to the x function was indestructible, right, when we take a derivative. The only difference is we have a modifier. We multiply by the natural log of whatever this base number is. So that's the only real thing that's changing it. It stays indestructible, but we multiply it by natural log of the base. Now, if this were e to the x, let's do a little aside here. If it were e to the x, and we were going to use this rule to apply to it, it should work, right? Because this is just another number, just like any number we can put in here. Then we would have the same exponential left over, e, or I should say e to the power of x, because it's indestructible, multiplied by natural log of the base, which is natural log of e. What is natural log of e? Natural log of e is 1, because e raised to the power of what number is going to give me e? Well, e raised to the 1 power is e, so it's going to be 1. So it's going to give us e to the x back. So this is the more general formula. This is the exponential derivative formula that applies to all exponential functions. Whatever number we have for a, we just keep the function indestructible and multiply by natural log of the base. It just so happens that when you have a natural exponential function with a base e, then when you apply this, this just goes to 1. So it's just indestructible, by itself over and over and over again. So we learned the special case first in the last section. Now we're opening our eyes a little bit to the more broad case. So 2 to the power